participants have joined, so we can start now. With your
Yeah,
permission, sir.
thank you so much for the kind introduction. So maybe we can start. And let me share my screen. Just I'm taking 1 or 2 minutes just for the setup part.
Sure, sir. Your screen is visible, sir.
Yeah, I use multiple screen, one for chat, one for teaching, so and all, just to keep things on the live. Yeah,
Yes, sir. I guess you have to ensure that audio is not connected on the remaining two devices so that.
sorry.
No, no, I was just saying in case if you are connecting via multiple devices, you have to ensure that audio is not connected on WebEx for the rest of the devices so that
Oh,
we don't feel echo.
uh,
For now,
all
it's fine. It's working fine
yeah,
already.
all devices are like connected to single CPU, so no worry. So
Oh, okay,
single.
okay.
Three
Yeah,
display devices, 3 display units.
display
Oh, okay, okay. That's
external monitors. Yeah,
Yeah, great,
yeah.
great.
Thanks a lot. Okay, let's start.
we can have separate session for that also afterwards.
I mean, we need to adapt. Like we learned these things during lockdown and everything, because that time I was continuing my PhD and I was like trying not to waste the time. So everything we had to learn how to manage time about internet. And although always like in-person's interactions always the best case, but we adopted the hybrid mode and it is not even bad. So you can utilize more time consuming thing because like more time efficient thing because it's digital. You did not do worry. Okay, thanks.
Right.
So so yesterday I got some. So basically, I'll start with the syllabus today with whatever that is stated in QT-00. I especially has taken the note. Okay, I have to cover these things: vectors, vector space, linear transformation, complex vectors, matrices, all these important topics. And then I realized that yesterday there were like some professors, some the audiences asked me like what are the applications in economics, applications in finance and all. So I can assure you that in QT-0001 as well as the other QT series, there will be plenty of examples, exercises, hands-on exercises, programming sessions, application sessions, which will cover in more detail of these things. But please keep patience and please keep note that this is not like a toolbox, like you have a chat GPT kind of thing, you give some input and quantum computer will give you output. Please do not expect these things. It has a different orientation, different insight. And like if you want to like just want to learn what is quantum computing, just Google it, that's enough. But if you want to learn the things, you need to go a bit slow because there are a lot of things we need to learn, especially the foundational part, mathematics, physics, some of the engineering stuff, and those will actually eventually help you after 3 months, 6 months that now you can confidently talk in quantum computing. Earlier those might be thinking a jargon, but now you have understood some of the important stuff and you can talk to these things. But to appreciate the like to motivate and appreciate those who are coming from non-engineering or non-science background, especially from commerce, finance, management, for them I articulated like a 5 minutes presentation talk on quantum computing, like and overall applications, just to motivate these things, and then I'll again go to the foundation in next 5-10 minutes. Okay, so today please keep patience because I'll cover some very basics things. Basics things means these are important for quantum computing, but many of you might think it as a like you already know these things. So please keep patience on for that part. But I'll try to connect in the end of the lecture that how those things are actually connected to quantum computing technology. Okay. Okay. So there is a question like set 2 cross 2 tensor product 2 cross 2. You please explain how 4 cross 4 working. Okay, please go through the notes. I have shown plenty of examples in the notes. Probably I shared two linear algebra notes, one for the beginners, one for the advanced, like postgraduate level scholars. I think there is 51 pages note I have written in hand. Okay, so Please go through it, all the detailed examples. I'm trying to just touch the topics here in this lecture because 1 hour, 2 hours lectures are not enough to learn algebra. I have taken my master's courses, PhD courses, still I am learning about algebra. Okay, so there are a lot of things to learn, but of course, I have given plenty of examples for the clarification. Please go through all those notes if you get time. Okay, so let's start with some of the overview of quantum computing applications. For example, so we know these things like what is quantum computing at least the basic fundamental of information processing is different here, right? So for example, like we do addition, multiplication, subtractions, the way arithmetic computation you do on a classical computer using the bit string 0 and 1. Here it is pretty much different. The basic unit of information, that is the qubit, represented in Ket 0 and Ket 1, which are vector quantities, right? And you can basically, what you can do there, this basically obeys the vector properties, various vector properties, scalar multiplication and vector addition. I'll cover these things in detail today. And certain matrix operations such as unitary matrix operations on these state vectors, right? So this is how actually quantum computing fundamentally is different from the classical computer. And by doing these things, n-bit representation, you can create 2 to the power n basis set. So it's a like exponentially increased space you can create, and accordingly you can store your information to probability amplitudes that alpha beta I was showing yesterday, right? So key areas that will be covered under the National Quantum Mission on this quantum computing, quantum communication, quantum sensing, and quantum material. I am focusing on this part, mainly quantum computing, but there will be specialized structured courses and topics which will be taken by the experts on quantum communication, such as QKD and all. There will be sessions on quantum sensing and meteorology. Please keep patience for those topics. Okay. So now we are interested about some of the people asked about what are the applications that might be there in the finance. Of course, there might be a lot of applications, but some of the interesting applications are portfolio optimization. So suppose how can a quantum computer analyze massive number of variables, right? So you have a lot of variables and potential outcomes simultaneously to find optimal investment portfolio that maximize returns. Suppose you have an objective function c of x, okay? How you can minimize or maximize this objective function. Suppose this is, if this is your profit function, right? So, okay, let me select one, maybe this one. Okay, maybe if it is your loss function, then you can minimize the loss function subject to certain constant, right? Subject to A, B, C, for example, A less than equals to something, say capital A, B less than equals to capital B, and C less than equals to capital C. These are the constant of your market, okay? And you want to minimize the things, right? So, okay. Today my screen is doing some problem. Please allow me 1 minute. Just let me connect it again. Yeah. So so if you want to maximize or minimize certain objective functions, right? Depending on your whether you want to maximize your profit, say profit function p of x, x are certain variables, and if the number of variables is so and high, so how you can optimize that given the market situation? So these kind of optimization problems, can you formulate a quantum algorithm for that or not, for a faster solution or a reliable solutions? There are applications like fraud detections and analysis. So given a massive set of data, can you train and test using a quantum machine learning framework such that you find the correlation among the various variables and parameters and try to indicate is there any fault in the data or not, like any fault activity in the data sets, like there is a fraud activity in the financial transactions or not, right? Okay, so I need to share my screen as well. Sorry. Is it visible now? Can someone confirm? Yeah, thanks. Yeah, so you can basically you can show basically maximization of certain profit function or minimization of certain loss functions, right? Portfolio optimization kind of problem. Or you can find certain fraud detection. So if there is any financial transaction fraud or not using various quantum machine learning framework, right? So these are also trading problems. So there are lots of problems whether you find that there are lots of variable x, right? Such that it is very difficult to understand some function on that variable f of x, right? Can you use a quantum computer to understand various aspects on fx, right? So those are various financial applications. So so let us give one example here for elaboration. Say, for example, for a commodity X and say 2 amount of X of X1 commodity plus 3 amount of X2 commodity, you set the price, say 10 rupees, and say 5 amount of X1 and 7 amount of X2, you set the price as 35, for example, right? And based on the market situation, suppose this is a very simple system like linear system, you need to find out what optimal value of the commodity X1 and X2 should be set, right? These are like class 6 level problem. Now, you can always formulate this as a matrix problem, like 2, 5, 3, 7 is a matrix, and your variable X1, X2, and your market price distribution 10 and 35, right? So it's a simple matrix inversion problem, X1 and X2, right? This is how your financial problem you can map to linear algebraic or differential equation kind of problem. And then you see whether it is difficult to solve by a classical computer or not, first of all. If it is solvable on a classical computer, you should go ahead. But like big companies like, say, various banks and all, they have a lots of such variables and lots of customers, right? So it is very difficult to solve them by a classical computer. Can you take advantage of quantum computer or not, right? So these kinds of applications are there for your quantum computing. You can look at. Then there are applications in other areas, especially scientific discovery. And one of the best application is the drug discovery, because if there is certain disease, right, some disease D, so there may be like combinatorial optimization problem. Which drug is the best drug that can act on the disease D, right? So there are like the space of D, like how many possibility of the drugs are there, and once you apply the drug on the disease D, what may be the impact, right? I. So these combinations of drug or the possibility of drug or the sample space of the drug is huge, right? Sample space of the drugs or the how to design the drugs, the elements that is required to design the drugs, especially certain proteins and all. So that is a huge combinatorial optimization problem. So can a quantum computer help to solve those kind of combinatorial optimizations problem or not, right? So that is one prominent application. So people are working on this. Various medical companies like Cleveland Clinic, in India, ICMR and all are working together with industries like IBM and others to design certain new drugs to disease like various RNA-based or DNA-based viruses and bacterial attacks on human body, right? Similarly, research on material science, can you design certain materials with a given set of behavior, whether it's a new alloy, new solar cell device or something like that, right? Or a new quantum materials, which can basically show quantum basically behavior in the different temperature, pressure and other environmental situations, right? So this is one prominent applications. I'm going a bit fast here because there is nothing to teach, nothing to as such important, but these are just motivation. So I'll go much slower in the mathematics part. Similarly, one important application in agriculture, there are many way you can think quantum computing in agriculture and sustainable technology, especially nitrogen fixation, right? So which is the best fertilizer for your agricultural field that can yield very high amount of agricultural growth, it can process efficient agricultural process such as the Haber-Bosch process, right, for ammonia production. So which is significantly consuming huge energy, right, to solve this Haber-Bosch process. And also it does a lot of greenhouse emission, right? Can you find a better method using quantum computing for this kind of applications? So now today there is a lot of issue with this markings. But not happening. just allow me a minute. Okay. So then there is the other applications like climate modeling, particle physics, cosmology applications, weather forecasting. So there are various ways how you can find numerically intractable problem, and you can basically, the purpose of quantum computing is to solve the numerical problem efficiently, faster. That is the main purpose of computing, quantum computing, and the main purpose of quantum communication is, can you transfer the information securely? Okay, so that will be covered sometime later. Okay, in this course. And there is a new like kind of you can say application that is a very nascent area. People are working on it. Still, there is no prominent result, but promising. There are various promising theoretical results, and some of them are tried on a machines like hardware. So this area is the quantum machine learning, basically, which is fusion of the machine learning and the quantum computing, or the AI and quantum computing, because AI is good for like training, right? Training means or learning from data, but it requires huge data. I mean, if there is a complex learning task, you need huge data, right? So there is a like various aspects how you can improve AI activity using quantum. Similarly, there are actions in the quantum part as well. Can you use AI for the betterment of quantum circuit design, quantum operator design, state design, etc. So both way, machine learning can help AI, machine learning can help quantum, as well as quantum can help AI. Enhanced optimization problem, better pattern recognition, or faster training. And applications include like medical image analysis such as fMRI, CT scan, X-ray, etc. So one of the ISRO scholar like 3-4 months back came up with a good idea to work with me on X-ray image analysis on quantum. So I didn't have much time to give him, but yeah, I mean, people are exploring those kind of applications as well, X-ray, CT, MRI, whether can you better detect certain like diseases or certain fractures or something like that. So logistics and supply chain. So this is much related with the finance and the management application. So like, what is the most efficient route for your travel path design, or various like your production, right, and supply chain, right, for numerous variables present in the market. Some of the variables may be volatile, dynamic. Some of the variable may be statics in the environment, right? And fraud detection, just I told, right? So I already shared this material with Professor Pillai sir, and he'll be sharing with you. For more information, you can visit this one. Last year, we articulated one prospective papers on various applications, hardware, technology, everything on this perspective research paper from IBM Quantum team, and this is also available online. You may have a look. Well, so today we'll start from here. I'm taking a 2 minutes break, and we'll start from this part. If you have any question, please feel free to ask in the chat, and we'll go over through this mathematical part now. Is there any doubt or anything? I hope my voice is audible, right? Yeah, thank you, sir. Okay, thank you, everyone. So, although, okay, what is the meaning of outer product? Okay, very good, good question. So today I will start with a very like class 6 level thing. Even if some of the participants are from bioinformatics or biotechnology side, they will, I hope, also not face difficulty. So that's why we'll start from very basics, and these are the syllabus, right? So don't worry, these things are also there in much detail in QT-03 as well. So there, me or somebody else will cover these things in much detailed version, but today for now, I'll cover some basics part and I'll touch each and every topic today. Okay. Yeah. So let us start with something that probably we learned in class 1 or 2 in our nursery school, right? Number system. And let us start from there. So please bear with me for now. What is the time? The time is 3:23. So please bear with me for 1 hour. In the middle, I'll give a break for 5 minutes, at least 1 hour at least, because I'll cover some very basic mathematics. This will help. I know many of you already know these things. Of course, you will be knowing these things, but it may be helpful for the people who are coming to quantum computing. They might not have these basics earlier, or they may forget these things sometime before. Yeah. So the number system, like we learned in our schools, like numbers, these numbers are positive numbers, right? Like 1, 2, 3, something like that. And we call it by the set P, right? Positive numbers. We learned about the natural numbers n, right? So for example, the numbers 1, 2, 3, and so on, right? You can in the positive numbers, you can take fractions as well, like 1.1, 2.2 as well. And then we learned about the natural number. So on. So the notation is please try to stick with the notation, because I'll be using various notations now onwards. Okay. Then there is integer set. Also, you can take the whole number, just whole number with both minus and plus. Okay, let me write that as well. Whole number. So whole number, you can write it as, say, in G. Normally, G is also representing the integers as well. So it is, say, something 2 minus 3 minus 2 minus 1, 0, 1, 2, 3, 1, 2, 3, and so on up to infinity, right? And typically, for positive integers, we write it as G plus, right? Or I. Sometimes it is also written as I plus. And there is a rational number. So the objective is to basically start with the very basic, and then I'll be reuse these notations. Okay, rational numbers. So these are written as fractions. So Q equals to M by N in the ratio, M by N ratio, right? So M can take any value in Z. And N can be some P, right? But N won't take 0. Okay. So then there is real numbers. This is important. Real numbers will denote by R, and real numbers can be any numbers in Q, right? And with the irrational numbers as well. So all numbers in Q are real, plus union means plus all the irrational numbers like square root 2, E, pi, all these things are in the real set. Okay. And we have learned all those things, okay, in our school. So now, if there are certain equations and we come up with something like, say, x square equals to 1, right? This kind of equation. So we can easily say, okay, I can solve these equations because x equals to plus minus 1, right? But if I give you some equations when it comes like x square equals to minus 1 kind of form, right? Because there may be scenario where x square plus 1 equals to 0, this kind of form can come into picture, right? Then you cannot easily say the value of x, right? That's why people discovered a number, and they call it that square root of minus 1 is some number, and we will call it as an imaginary number, right? Imaginary number. Yeah, so whole numbers denoted by W. It's just notation, like standard notation. Sometimes W, sometimes Z. It depends. Various textbooks use something, whatever you feel suitable, use that. So in general, we will mostly use the real number, imaginary number, and the integer throughout the quantum literature. So whatever you feel suitable, you can use it. Okay. So then Then basically you can just say, okay, x squared, then x I can say square root of -1, right? And from that I can say, okay, this is some imaginary plus minus imaginary or imaginary value I, right? So based on that, different number system came, and that we represent by a variable z, where there is a real part, okay, and there is an imaginary part I times b. This is the imaginary part. Imaginary part. So a pure imaginary number will have a equals to 0, which will be a pure real number. And if this part equals to 0, right, that will be pure, sorry, this will be pure imaginary actually. Imaginary number. And if this part is 0, that will be pure real number, right? However, you can represent always any real number equals to some real value plus I times 0, that way as well, right? That option is always there. So, that means there is another set of numbers, and we denote it. All those numbers where you have a real component and an imaginary component will denote that set as C, set of complex numbers. Complex numbers. And all the probability amplitudes in the quantum state representation will be numbers which will be taken from which. So any quantum, so any probabilistic state in a, say for example, ket psi equals to alpha ket0 plus beta ket1, right? This alpha and beta, they are the set element of this C. So we typically denote it as alpha beta belongs to C, this way, right? So we'll be using this notation frequently, okay? Now, there are certain important relations we need to know, because complex numbers are denoted in the, represented in the complex plane, circular complex plane. So this way, so let's define two-axis system. You need always some reference system to represent informations, right? So any vector, that vector you can say a plus bi. What does it mean? The along the horizontal axis is the amount a, right? And along this axis, the amount is b, right? If you call it a real, this is a z plane. This is real part of z, and this is the imaginary part of z, right? So this is some x-axis and y-axis, something like that, right? Now, if this angle is theta, right, and this is a right angle triangle, if I join this line, so if it's a right angle triangle, so you can easily say that this a equals to, and if this is equals to r, right? So what is this value? This value is r cos theta, right? So what is the definition of cos theta? The definition of cos theta is base by the hypotenuse, right? So then hypotenuse equals to base into cos theta, right? So a will be r cos theta by just simple definition of cos theta, because cos theta equals to, those who still have confused, cos theta, the definition of cos theta equals to a by r, right? So your a becomes r cos theta. Similarly, you can calculate b equals to r sin theta. So just we have learned that z can be represented as a plus ib. So it is equivalent to, we can write as r cos theta plus I r sin theta. That means r I can take common, cos theta plus I sin theta, right? This is the same expression, okay? So this theta is important because you will operate on quantum state, you will do rotations, you will do reflections, many other things. So complex number will be just a handy tool, right? And in this complex number theory, you need to just know one more thing, that is called the Euler's formula, okay? Euler's formula. The formula is e to the power I theta equals to cos theta plus I sin theta. I'm not giving a proof of this Euler's formula, it's a theorem. So once I say e to the power I theta equals to cos theta plus I sin theta, immediately what I know that g can also be written as r e to the power I theta, right? So what are the form of complex number we just learned? That z can be written as r I theta, z can be written as a plus bi, z can be written as r cos theta plus I sin theta. So these are the three different forms So this is in exponential form. This is in also you can say trigonometric Euler form. It's a trigonometric form, and it's a simple arithmetic form, right, or algebraic form, you can say. So these are the three representation of Z, right? So this is important because many times when you need to operate on quantum state, you want to detect certain phase or you want to estimate certain phase of a quantum state. So this form will be required. This will be important for you, right? But of course, there are gates which you can design with cos theta, sin theta as well. Okay, so there are certain things later you will see it. So now this is all about complex numbers. Done. Can someone confirm that? Is there any doubt or anything? Like, do you need me to repeat anything? I'm audible, right? Okay, fine. Thank you. So now let's go to vector space, right? So this is not a difficult thing, but any interview you go across the IITs, across IISc, everywhere people will ask you this question: what is a vector space? Whenever you say somebody, okay, quantum algorithms, quantum information works on Hilbert space, immediately they will ask you what is Hilbert space, and you come back to, okay, this is some vector space with certain properties, and then immediately they will ask you what is vector space, right? So let's start about vector space, and especially for the quantum part, we need to know complex vector space, right? Okay, great. So whenever you define or you say vector space, right, it involves two sets. So it involves two sets. There are two sets of numbers basically. So one set is V and another set is F. Okay, with two different operations. There is two sets and there are two operations, two kind of operations. What are the operations? One is called the vector addition. So yesterday somebody asked me, can I add two numbers, 2 plus 3 equals to 5 in quantum computer? This seems to be a very like mad question or something, but actually it is a difficult question, and I'll come back to the direct answer is addition is not a valid quantum operations, but I'll prove it using this vector addition principle towards the end of this class. So vector addition is denoted by this plus, right? And this is the you operate some element, you take some element from the set V, and you does the operations on another element of that element on that set V, and whatever element you get, that is also a element on V, such that I'll give example, don't worry. So these notations I'll use and I'll give example, plenty of examples. Okay, such that if you take two vectors, say small v vector, okay, let instead of the small v, let's take x and y, x plus y belongs to the set V. So what this first theorem says, if x belongs to the set V, if y belongs to the set V, and if I add these two vectors x and y, okay, whatever result I get, that is also belongs to the set V, right? So if I do vector addition, so you leave these things. Your notation initially you may feel bad for this, so leave these things. Okay, slowly in the notes all these notations and everything are there, but for simply let us try to understand. If you have two vectors and those vectors are the element of a set, the set of vectors basically V, right? Then if I add these two vectors, whatever result I get, that should be also an element of this set V, right? That is the first property. Okay, so this is the first property is called the vector addition property. And the second one is, so second property is called the scalar multiplication. Scalar multiplication. So if there is a scalar, say A is a scalar quantity like 2, 3, 5, 6, 7, right? Any scalar quantity. and that belongs to the set F. So F is a basically field of scalar numbers. And this is the set V is a set of vectors, right? Belongs to the vector field. This belongs to the scalar field. I'm not defining what is field and all because of the audience, like the diversity of the audience. Maybe we'll come back later sometime. So if A is some scalar and that belongs to F, okay, and W is some vector, say, and that belongs to the set V. If this is the case, then A into W, right, will belongs to the set vector, right, V. So what I mean to say is that suppose you have a vector X, right? X is 1, 2, for example, X vector, right? And say Y equals to 3, 4, right? So if I add them like X plus Y, so it will be element wise addition. 1 plus 3 will be 4 and 2 plus 4 will be 6. And this X plus Y vector, whatever result I get 4 and 6, that should also belong to the set capital V, right? Now what it says, this is the first property. Second property, it says that scalar multiplication, like if I choose some scalar value, say 3 times some vector, say 1, 2, right? What result I'll get? 3 into 1 will be 3, 3 into 2 will be 6. I get 3 and 6, right? This particular vector with element 3 and 6. Now this should be a vector and also belongs to the set V. So this is the set of vectors, this is the set of scalar, okay? So these two important property should actually hold for the vector space. Now I have taken real numbers. See, 1, 2, 3, 4, 4, 6, 3, 6. All these are real numbers. Once you have a complex number, say the vector is V equals to 1 plus 3j and 2 minus 2j, for example. So these elements are now belongs to the set this C, right? Then directly V will belongs to the set C 2 cross 1. This is then we'll call it as a vector space, complex vector space. Earlier the element was belonging to R, right? So 1, 2, 3, 4, these are R. That time this V bar was the set. This is basically the real set with dimension 2 cross 1, right? So if you have a vector, so what is a vector? Okay, so let me define a vector first, okay, because vector space requires the definition of vectors as well. So what physics says in our class 9, 10, 11, 12, we have learned that if there is a length and there is a basically direction, right? So in 2D or 3D object, we call it as a vector, right? Say for example, 2 plus 3j, right? Or 2i plus 3j, yeah, something like that, okay? What computer science says? Computer science says list of numbers presented in one-dimensional array, that is called a vector, right? For example, 2, 1, right? 3, 0, minus 1, minus 2, right? And so on, right? This is the definition of vector in computer science. In fact, it is a column vector. If you write this way, 1, 2, 3, 4, up to 100, say for example, this is a row vector. Okay, yesterday we have seen these things. And this is a column vector. In fact, what physics says, if you write this way, 2 and 3, it becomes the representation in CS way, computer science way, the same vector thing. So it's just a one-dimensional array, okay? And so now you might have things like it should the objects which should follow the vector addition and scalar multiplications, right? That means scaling by a factor called scalar, right? So then basically that is the way how mathematics defines these vectors and vector spaces, right? So if you have a big number, say x equals to say 1, 2, 4, 8, right? 16 up to say 1024, right? So I have written this number as 2 to the power and the index I, right? As the number series. As you increase I equals to say 1 to 10, then you get this series of numbers x bar, right? Now you have how many dimensions are here? How many numbers are there? There are 10 numbers. So this immediately, this x bar vector has the dimension R 10 cross 1, right? And you cannot represent this number on a 2-dimensional, 3-dimensional case. However, we typically write it, we draw it, but in general, it requires to represent 10-dimensional space for these vectors, right? But I mean, if you just define it on a plane, you can put like this thing. But once we'll go for the matrices of say 4 cross 4 or 10 cross 10, you cannot represent them easily on a geometry, right? Okay, so we defined what is vector, right? And now we have to go for some more things, especially as per syllabus, there is something called linear independence and other things. Let's go with that. Linear independence. Okay, even there is also thing like I have said vector additions, right? So if I take alpha amount of scalar amount of this vector x and beta amount of this vector y, and I should get as per the second law of things vector space, whatever I get. So that is some another vector, say z, right? Z is another vector. And as per definition, that should belongs to V. This is exactly what it is called the quantum superposition theorem, right? Simple linear combination of vectors, right? Now there is some additional condition of alpha and beta coming from the quantum postulates, right? That is a different part, but in general, they are vectors, right? How we represent the informations, right? I will see more about the alpha and beta tomorrow in the probability session. Okay. So we were talking about the linear independence. Now suppose you have a set set of vectors, right? Many vectors, right? V1, V2, V3, and so on. All these are vectors actually. Vn, and we call this set that is a subset of the bigger set capital V. We say that these vectors 1, 2, 3, 4 up to n, they are linearly independent. The set is linearly independent, or these vectors are linearly independent. If some combinations like A V1 plus A2 V2, say A1 V1 plus A2 V2, so on An Vn, the linear combination of these vectors will produce zero result, right? If and only if A1 equals to A2 equals to dot 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 equals to An equals to 0. So other than 0, if I choose any other element, it will be non-zero. If that is the condition, then we say they are independent. And if this does not validate, then we'll say they are the dependent vectors. For example, let us take an example to understand these things. Suppose I take two vectors, say 1, 2, 3. This is one vector. And another thing is 2, 4, 6. This is another vector, right? And I take another vector, say 3, 5, 6, right? And this vector I call V1, this vector I call as V2, and this is V3. You can see if you take a combinations like for these two vectors, right? Say 2 amount of V1 minus V2 if you do, right? So minus 1 time V2, you can easily check this is 0, right? Even by taking non-zero coefficient, I still can get the 0 result. That means the second V2 is just the double of V1, right? That means these two vectors are dependent. Now you take V2 with V3 or V1 with V3, you cannot represent V3 as some like some amount of V1, right? So that means V1 and V3 are independent, but V1 and V2 are dependent, right? Okay. Now there is something called the basis and dimension. So what is basis? So a basis is basis of a vector space, and that is the bigger set V, is a set of linearly independent vectors that spans that total vector space V, right? And the dimension of this basically vector space V is denoted by dimension of V in this way, right? So let us take an example for R3 space, right? So let's take X, Y, and Z. This is the three-dimensional space we know, right? This is X-axis, this is Y-axis, and this is say this is Y, and this is say Z-axis, right? Now, if I take a point here and the elements are say 1, 0, 0, right? And here I had in Y it is 0, 1, 0, for example, right? It's a point where X-axis is 0, Z-axis is 0, and Y-axis has the amount 1. Similarly, here it is 0, 0, 1. The Z-axis amount is 1, but X-axis and Y-axis are have length 0, right? Now, if this is the case, right, then any vector you choose, right, R vector, which can be basically formed using the combination of these three fundamental or the elementary vectors, right? They are independent of each other. So you cannot represent this vector using this or this. So these are highly basically independent, right? They are independent. So now you can form any vector using these three fundamental or the elementary vectors. That's why this R vector will depend on these three things. But individually, they are the basis that form this vector space, entire vector space R3, right? Similarly, on the quantum computing, we have seen we need in a this blosphere case for a qubit, it is as 1, 0 and it is as 0, 1, right? As the basis. Any quantum information you can represent as gate 0 plus gate 1 form, right? So any quantum state you can represent some amount of gate 0 plus some amount of gate 1. And there will be some additional condition of A and B. Okay. Yeah. So actually, I would use the various colors, but somehow my digital board is not working. So I am directly using the presentation mode to write this. Sorry for that. So there is always some technical glitch in the devices. Okay. Now, let's see some more coordinates of a vector. This is important. Coordinates of a vector. Somebody is saying you are not audible. Can someone else confirm? Yeah, I'm audible. Thank you. Coordinates of a vector. So if I can represent any vector or quantum state V as A1 V1 plus A2 V2, right? All these A1 A2, these are scalar quantities, and V1 V2, these are vector quantities. Okay. So sometimes I represent vectors as bar. In quantum, this is written as Kate notations, right? Some books write in different way, like small letter with bold size. This is IEEE format. Okay. So whatever things you prefer, but in general, a quantum state, all the properties of vector will hold. In general, this is a simple column vector, right? Column vector with normalized coefficients, with normalizations. Okay. With the normalizations means norm of this vector V will be equals to 1. Okay. This is the some additional property. Everything else, whatever you have learned in linear algebra will be useful. Okay. So suppose we have some vector V, which is represented as A1 V1 plus A2 V2, so on A1 AN Vn, right? And these are all the scalars, like scalars here. The scalars are A1, A2, means these are just some fixed numbers. Okay, AN. These are called the coordinates. Are the coordinates of the relative to the basis. Now let us relate it to the physics part first, and then I'll relate it to the quantum computing part. So those who are facing with video and audio, one suggestion is please rejoin. Sometimes your internet connectivity faces issue, so it common. So please rejoin. and I'll also share the notes, no worry. So in school physics, we have seen if I represent a vector like this, say 2i plus 3j, right? So the coordinates are 2, 3. That's why you can write this as a column vector 2, 3, like 2, 3. It's a column vector, right? So these 2 and 3 are the coordinates, right? Because exactly if this is x-axis and this is y-axis, right? And you draw like a plot, like quadrant, first quadrant, second quadrant, third, fourth quadrant. In the first quadrant, you will see this is the coordinate are 1, 2, 3. Exactly how maps work, right? Digital maps, Google Maps works in this way, right? Like the process information, Google process using these vectors things, but whatever you see, like the latitude, longitude thing in this coordinate forms, right? So this is how it is related with the physics and math. Now let's connect it to the quantum computing part. Suppose we represent some quantum state as C0, 0, 0 plus C1, 0, 1. These are bases only, right? C2, 1, 0 plus C3, 1, 1. You have used 2 qubits to represent a quantum state psi, right? So your circuit will look like this. Gate 0, gate 0, okay? And you have some circuit here, right? So ultimately, at the output, you have gate psi equals to this state. Some C0. So what are the combination of these two states? 0, 0, 0, 1, 1, 0, and 1, 1. These are the 4 possible combination of from the tensor product of 0 and 0 you can create. These are the 4 maximum possible configuration you can create, right? In the 2 qubit settings. Then whatever applications you do here, after that, suppose you get C0, 0, 0, C1, 0, 1, C2, 1, 0, and C3, 1, 1. This is your quantum state, right? So the coordinates we normally, this is equivalent to represent as C0, C1, C2, and C3. What does it mean? This is in some space, like in a 4-dimensional. So of course, it belongs to now C4 cross 1 column vector, right? I should write it as a transpose. Like transpose means it's like just this way you can write, right? So basically C0, C1, C2, 3, C4, C0, C1, C2, C3 is the 4 elements are here. These are the coordinates. So basically, if I could draw a 4-dimensional space, something like this. So 0, 0, 0, 1, 1, 0, and 1, 1. These are 4 basis states, right? And there are certain probabilities or amplitude. So C0, C1, C2, and C3 related to that, such that square of these things, C0 plus C0 square plus C1 square plus C2 square plus C3 square equals to 1. This is the coming from the quantum postulates, like sum of Ci square for all I equals to 1, right? This is coming from the postulate, but you can represent this information in this way, like column vector C0, C1, C2, and C3, which is a 4 cross 1-dimensional vector space, right? Complex vector space, right? So it's basically, it's a vector belongs to a complex vector space, right? So this is how you could represent quantum information in this way. I'm going very slow, very basic things, obvious things, right? But so that whenever you go to the big algorithms or anything, you don't feel like it's something very mathematically intricate or something, but these are not that difficult. Now, we have done the basics things that if we want to represent anything, whether it's a vector, any informations in the quantum mechanical picture, it's a vector quantity. You need some basis, right? Here they are computational basis. Sometimes you will also see I can represent information in Fourier basis, eigen basis, wavelet basis, other basis as well. But for now, we are stick to the computational basis 0, 0, 0, 1, 1, 0, 1, 1. Okay. Now there is one topic on norm, inner product. Inner product yesterday I covered, but there was one question by someone, what is outer product? Okay, I'll go to that part. And there is orthogonality. Okay, this color is might not be suitable for others, so let me change the color. Okay, let it be black. Norm is one very important topic. So today it's difficult to cover the entire norm because only teaching norm will take 1 or 2 classes. So I'm just giving a very overview of what is norm. Okay, a norm is a function. Basically, it's a function that assigns non-negative. Basically, it's length. Okay, it's a non-negative length. Length is non-negative, so a length or size to a vector quantity. So if you have some quantum state, you of course need to calculate certain things. And norm is something that will help you to calculate certain lengths or fidelity and other things of a quantum state. Okay, so it is denoted as if there is a vector v, and the norm is denoted as norm of v, right? Now it has various types and various properties. So typically, first already I said it's a non-negative. So of course, then you can directly write that it is greater equals to 0. It will be 0 only if v vector is a 0 vector, then only norm of v is 0. Else it is greater than 0. Okay. And all other properties, I'm not going like triangular inequality and other property, but Chebyshev's inequality, some of the things are there. Suppose, for example, there is a vector u and there is a vector v, norm of them will be lesser equals to norm of u and norm of v, right? So this is called the triangular inequality. Later you will find the Chebyshev's inequality and the triangular inequality, Schwarz inequality. All these will follow this norm property and also I'm not going to that directions, but what is important is that the context. Um, Context is at least we need to know one or two norms, but in when you do quantum experiment, you need to know other norms as well. So first, let us understand what is norm one, what is one norm, and what is two norm. There is geodesic norm, however, which is the shortest route when we want to travel between Delhi and Bangalore using a flight. What is the shortest route? For that, these are not the best length. Then you have to use geodesic norm. Okay, so it has a different definition. In quantum also there will be various norms, but these two are very frequent. So this V2 norm we have learned since our childhood, school, everywhere. This is also known as Euclidean norm, Euclidean distance. Okay, Euclidean distance or Euclidean norm. So suppose you have two vectors, right? Say x1 one vector, x2 another vector, right? And component is, say for example, it has the component 1 2, right? Or in fact, let's take a better value, 4 2, and it has a value say 3 1, right? And we have learned Euclidean distance. This two norm is defined as this two norm is defined as summation over vi square root. Okay, when you have two component, so I have taken two component here. Individually you can compute it, but in general you want to compute, suppose the difference between these two state x1 and x2 of these two now, what is the distance between these two vectors, right? Then x1 minus x2 is the this vector, right? Using the triangular law, so it will be equals to your 4 minus 3 square plus your 2 minus 1 square, right? Square root 2 is the answer, right? This is what we have learned from our childhood, and it certainly it gives many advantage to calculate Euclidean distance, to compute the distance between, say, two quantum state, distance between two like the closeness of certain two features, right? So certain two elements, right? But often there is a very popular norm in machine learning, this V1 norm. Let me go to that part. Suppose whenever you are traveling in a road actually, so the road maybe looks like this, right? And there, so you can always say, okay, if I go from place A to place B, right? So in this way, of course, that will be the like Euclidean norm you can calculate, and I can say I can always go this way, like directly A to B. But in a physical road, like the actual road, like when you go by bus or train or by bike, some vehicle, right? You may not get this kind of path because there will be trees, buildings, and other things. So you need to go this way only, right? So that's why you need to add this distance modulus plus this distance modulus plus this distance modulus
plus this distance modulus and this distance plus this distance and so on, right? And this particular norm is called one norm. Okay, so individual component, you need to take the modulus and sum them, right? So it is inspired by the city, Manhattan. That's why another name of this norm is called the Manhattan norm. Okay, and this is very, very popular in machine learning literature, AI literature. Okay, so for computing various problems like shortest path algorithms and all. Similarly, a Euclidean one, geodesic one. So geodesic means our Earth is round, right? Something like this. So if you want to travel from say New York to Tokyo, right? So you cannot simply like go like this. So you have to fly this way. That's why traveling routes are like this only. So, I can prove this, but not today. So you can always check that the geodesic distance, like the oval kind of distance, geodesic distance, in fact, it's much lesser than the Euclidean distance in this particular case. Okay, so because of this spherical coordinate system. Okay, so these are various cases, and similarly, let's today even before ending the class, I'll show you that if you have a quantum state psi, it's a vector basically, right? And if you have another quantum state phi, in fact, you can calculate the two norm of these two vector. That means how this quantum state is very close to the quantum state phi, or how similar these two quantum state. Suppose you do some experiments, right? And you get some result, some resultant quantum state, right? But actually, what was happening, or there is a like a ground truth, right, to that situation is phi. Now, whatever experimental result you have achieved, how close is it to the ground truth, right? You can calculate the Euclidean norm of the two norm or the quantum closeness. This is also known as the fidelity, quantum fidelity. Okay. So the notation will be something like this, this and phi this way, or you can write the vice versa and this, right? So just the notation will be different, and this is called the quantum fidelity. So this is basically a two norm of vectors, quantum fidelity. And I'll show what is the circuit for calculating the quantum fidelity towards end of this class. And just let me just complete the inner product, and then I'll give a break. So just 2 minutes only. Inner product, outer product, both will check because there somebody asks what is outer product, right? Okay, so there is something called tensor. Okay, this is like a quantity, and if a tensor has rank of basically 0, it's a scalar quantity. It has a rank of 1, it is called a vector quantity. If it has rank of 2, it is called basically scalar has no dimensions, right? So it has rank of tensor of rank 0. It is a tensor of rank 1, means vector is one dimensional. Then matrix is basically it is also a tensor of rank 2. That means it has two coordinates, row and column. Similarly, there are various like how we represent the informations in scalar form, vector form, or the matrix form. So we just learned that scalar can be represented by R, vector can be represented by Rn cross 1, right? Some n number of element if it has, and matrix you can represent as Rn cross n if it has n number of columns, n number of rows, or m cross n you can write for a rectangular matrix, right? So there is a, for those who are bit new to algebra, there is a relation. Let me tell you. So vector, say let's take two vectors, say 1, 2, and another vector, say 3, 4, right? So if you to multiply these two vector, what is the dimension of this first vector? 2 cross 1, right? And what is the dimension of this thing? Like how many things are here? 1 cross 2, right? So if you multiply these things, what I'll get? 1 multiplication with 3, 3. 1 multiplication with 4, 4. 2 multiplication with 3, 6. 2 multiplication with 4, 8. So if I multiply like a row vector times it's a row vector, right? It's a row vector. So let's call it x, right? And let's call it y, right? So basically, if you represent a vector in row vector form, right? And similarly, you can always write it column vector as transport form. This is a basically column vector. column vector. Similarly, you could write x transpose as like this way, right? 1, 2 as column vector form. Column vector form, right? So when I multiply x, y star, this is the outer product. Okay, so I just did a mistake. Thanks for letting me know. Okay, so this is like the opposite one. Okay, just let me go to the next page, maybe 1, 2, and this is 3, 4, right? So this is 1 cross 2, correct? So because there are 2 columns and 1 row. Thank you for letting me know. And there is one particular column, right? And 2 rows are here. So basically it is your 2 cross 1. Thank you. So I'll get 1 times 3 is basically 3 plus 2 times 4 basically 8, right? 11. So I get a scalar quantity, means 1 cross 1 is a scalar quantity, right? Right. So that means if I multiply a row vector times a column vector, right? So row vector times a column vector is basically a scalar quantity. It is written as x star y or x transpose y in this form, right? Or also denote the notation is x, this ket notation, right? X and y. This is called the inner product. Now, if I do the reverse things like 1, 2, and 3, 4 in this way. So now it has 1 column and 2 row, right? So basically 2 cross 1, and this is like 1 row and 2 column, right? So 1 cross 2, and it will be a 2 cross 2 matrix, right? So the earlier example that I wrote wrongly, this one 3, 4, 6, 8. So it will be 3, 4, 6, and 8, right? So this will be your matrix things, right? So if you multiply if you do dot product of 2 vectors, you will get a scalar quantity. If you do outer product, that this particular orientation is called the outer product of 2 vector. So it is written as x y star form or x y transpose form, or in fact x y this notation. Right. So let me write it clearly. So this is written as outer product x y this way. Right? This is a ket and bra. Okay, column vector times a row vector. Is it correct now? Can somebody confirm? Thank you for letting me know. Yeah, thanks. Okay. So as we are human beings, we always do this. Yeah, it does not. Okay, maybe they are more erroneous or they may not be. Okay, so the inner product we learned this way, and the outer product is basically is a row vector times a column vector, and it's vice versa. This is the outer product, right? So outer product is basically a matrix, just we have learned. It can be some R or C, basically. It can better to write C because it's a complex numbers in quantum, n cross n, and it will give you some C complex numbers, basically. Right. With this, I am just concluding here for 5 minutes because there might be recording or something. So I'll come back at 4:15. Thank you. So we have to do diagonalization, eigenvalues, yeah, and orthogonality. Fine. Okay, thank you for your kind patience. And okay, so just one thing was remaining in the previous slide. So let me first complete that. That is called the orthogonality or orthogonal vectors. So if you have two vectors x and y, and if you do the dot product, right? So they will be set as orthogonal vectors. So as soon as they are, of course, you can consider they are non-zero. So they the inner product, if the inner product is zero result, then you can say that the vectors x and y are orthogonal vectors, right? Orthogonal vectors. So in fact, some of the cases will say ortho. So if x and x and y give the dot product gives the result 0, as well as x is normalized, norm is 1, and y the norm is 1, right? Then and also they gives the inner product x and y equals to 0 with this additional condition, then we'll say they are orthonormal basis. Orthonormal basis. So if the vectors are normalized as well as their inner product is 0, we say orthonormal basis vectors. And if they are not orthonormalized, they are not normalized, but the inner product is 0, we will say they are orthogonal vectors. For example, this ket0 and ket1, the fundamental unit. So ket0 is your 1, 0 vector, column vector, and 1 is 0, 1 column vector. So you can say individually the norm is 1, right? As well as if you do the dot product between 1, 0 and 0, 1. So these two state ket0 and ket1 basically. You'll see this is equals to 0. Just simply 0 into 1 plus 1 into 0 equals to 0. So you'll be getting that they are both normalized as well as orthogonal. So they are called orthonormal basis vectors in quantum computing. Can you say the expectation value probability of a state? Yeah, tomorrow there is probability session I'll cover. Please ask me the question again. If I forget, I'll come back. Now, let us start something interesting. And we have additional around 30 for 35 minutes. So we'll go through some interesting stuff. Now let's go back to physics again. And then we'll do the journey and we'll come back to algebra again. So let's start with the Schrodinger equation, right? Because it connects the evolution of the description of the wave function and how it evolves over time, and the equation that we learned that it is I h bar del t, that is the time evolution of a wave function psi t. I'm not taking the ket notation now, so let's take psi is a function, some function of x and t, right? Equals to this is some function, wave functions, right? H is some Hamiltonian times the wave function x comma t. Now h you can write as a kinetic energy plus potential energy form or any other form, but in general this is the simplest form. So it's a ordinary differential equation, ODE, ordinary differential equation in time, right? So now if you solve this equation, right, and if you're Hamiltonian, this Hamiltonian, if you represent in matrix form, right, and this psi quantum state in the vector form. So what we get, the equations look like this: ddt of your ket psi xt, you can write it like this, equals to H is some matrix called some matrix, and this matrix is a Hermitian matrix. Hermitian matrix. What is a Hermitian matrix? I'll define it. Times the state vector ket psi xt, right? Now, if it is a ODE equation, you can always solve these equations, right? ODE equation, and you will get the solution as psi of x comma t equals to, we put the solve it and basically put the boundary condition by taking the space and time as independent to each other. And you'll be getting as e to the power minus iht psi of x comma 0 t equals to 0. Okay, initial state to the final state like this, right? Now I can write it as a Ket notation form this way, because this is now vectorized quantity or discretized quantity. So this is whatever quantum state, like this is now what is happening here. What is happening here from the Schrodinger equation? This is your initial state, which is a vector, right? Input. This is an updated state or evolved state. Evolved state. And this is also a vector, basically, right? And this is a matrix that is doing the time evolution. This is called the time evolution matrix. Now, whether it is time dependent, independent, those aspects I'm not going. But let us try to relate this picture with engineering. Suppose assume that something there is an input. Let's initial state that psi at t equals to 0. You are giving as input to a system, and that system has a characteristics of e to the power minus iht. H basically is called Hamiltonian of the system. That represent the dynamics of the system, how it evolves, how its energies are distributed and all. And whatever you are getting some output, this is the input, right? And the output is some state psi, some t equals to some t1, say for example, right? So in simple, what we get, our input is a quantum state, say phi at t0 basically. And then there is e to the power minus iht is a system, and there is an output is a psi state, for example, right? This is the input, this is the output quantum state. So what it becomes that, of course, if H is a matrix, then e to the power iht is some another matrix, right? And suppose we call it a matrix, say A equals to, say, e to the power minus iht, right? Now, if A equals to e to the power iht, that means your output state, get psi, you can always write as A into get phi from system description, from like any engineering system description, right? You have a like input that is operating the basically time evolution operator, that some matrix is acting on the vector, initial vector phi, and that is generating another vector psi, right? This is the initial, and this is some matrix, and this is the evolved, right? The same equation, just we convert it to linear algebraic form. Now, yeah, you can think as a transfer function, right? Now, we related the physics to the engineering part. Now what we have to do is, now we know that there is a fundamental equation called the eigenvalue equations, that is ax equals to lambda x, right? What is this equation? This equation is saying that, so suppose the matrix is suppose A11, A12, A13, A14. What a matrix does, it does the linear transformations, right? A rotation or reflection or perfect or the projection, whatever it does on the vector, say x1 and x2 are the element of the vector x. This is suppose x, and this is suppose A, and whatever. So this is a linear kind of equations, right? So this, for example, if it is a rotation, suppose you have a vector like this, this is your x vector, for example, right? And the coordinates are x1 and x2, right? This is the coordinate are x1 and x2, right? And you want to rotate it by the angle theta, suppose, right? So what will be my transformation matrix A? My A matrix will be cos theta minus sin theta, cos theta, right? This will be my matrix. Then I can get this vector. Suppose this vector is x, I will get the vector y. The y will be obtained as A times x, right? I'll get, because A is right now this one. So, but what it is saying that this is something, this is a special equation. In fact, this linear transformation Ax equals to lambda x is special. First of all, x has to be a non-zero vector. Then I will do a linear transformation on the vector x, but there will be no change in the direction, but there will be stretching in the vector. I can stretch it, I can squeeze it, whatever I want to do. That means I can scale it. I can scale the vector, but no change of direction. No change of direction. And this is fundamental, right? So, so this particular special relation x equals to lambda x, that a mathematical transformation A, if I do on the vector x, but the vector does not change its direction, only stretching is done, then this particular relation is called the eigenvalue problem or eigenvalue relation. Eigenvalue problem. All the musical note, everything, this equation is fundamental. Quantum physics, anywhere. Principal value, principal component analysis, everywhere you see, this is fundamental. This is very common. In fact, in some QT-03, we'll see much detailed version of this, why it is and how it is coming and what are the implications and all. Then there is not even a single x. There may be many such x, right? Say, for example, I can find out some vector x1 such that if I multiply with a, I can get lambda 1 x1. If I find another x, that is x2 for a, I can find another eigenequation x2 and so on and so forth up to xn. Then I can find lambda n xn. I can find many such x such that if I multiply the same matrix with it, I can get very different scalars that scale this particular vector x. Then the set of all such vectors x1, x2, and xn are called the eigenvectors. And those scalars which scale the vector x, lambda 1, lambda 2 to lambda n, they are called the eigenvalues. And in the first day, initially what I told that there is a corresponding operator applying on a quantum state that yields an eigenvalue, right? And that particular quantum state does not change. What I get is a discretized or the scaling factor of that particular wave function, and that is my desired quantity like positions, momentum, etc. Right? In fact, if this A is your Hamiltonian operator or energy operator, then this A will be equals to h bar omega or h nu, energy quantity, various discrete energy levels. So solving a Hamiltonian simulation problem gives you various discrete energy level of an atom or a molecule or a quantum mechanical system. And that is the fundamental question asked in quantum physics or quantum chemistry. So quantum phenomena. Okay. Now, let us relate these things. So I have written. I've written x equals to lambda x, right? So lambda is a scalar quantity which scales the vector x, but not the angle, right? Yeah, of course. There is much more detail on EVD, SPD techniques. So I'm just giving an overview because itself EVD can take 4 or 5 classes to explanation. I'm going a bit slow. Okay. So this part, x equals to lambda x. Now, if you multiply x star, right, and ax pre-multiplication with x, left side x multiplication and right side, because it's a scalar quantity, you can write a scalar quantity outside this part. So x star x. This is same. Like I multiply both side x star, like x star ax equals to x star lambda x, x star lambda x, say for example. Then lambda will come to front because it's a scalar quantity, so x star x, just a step jump, right? So once you can do that, and basically once x is a quantum state, that means your x, that is you can write as kx, is normalized, right? Equals to 1, normalized. That means this part x star x equals to 1, right? So we will have x star ax equals to some lambda, right? But you don't know like which lambda it is. It is the minimum lambda or maximum lambda, right? So either if you minimize this function x star ax for some x, which x you don't know, then whatever value you get is the minimum lambda, and this is related to the ground state of the molecule, right? So this is related to the or the minimum eigenvalue. So there are algorithms like variational quantum eigensolver VQE, which does these mathematical operations, right? Or QAOA, quantum approximate optimization algorithm. So all those things are based on this equation x star ax equals to lambda. Okay, and we'll come back in this course again and again. We'll come back. Okay. X star is the complex conjugate of x. Yes. So now there is a property that I initially state that A equals to e to the power minus IHT, right? And if H is a matrix, right? And that matrix, if it is Hermitian, those who do not know Hermitian, let me tell you, say, suppose H equals to, if it is a real case, we'll say it's a symmetric matrix. For example, 1, 2, 2, 1. These kind of matrices are called a symmetric matrix. But if the elements are complex, say H equals to 1 plus I, 2 plus J, 2 plus I, plus 2 minus, you can write 2 minus J, and you can write, say, 3, right? So if you take this part, so then you can easily check H star will be equals to your 1 plus I, and this part will go here with complex conjugation. So 2 minus J with complex conjugate, so it will be 2 plus J, and this part will come here. So 2 plus J with complex conjugation, so it will become 2 minus J and 3, right? So then this matrix is called a Hermitian matrix. And this matrix also, if you do H transpose, it will be 1, 2, 2, 1. This is called a symmetric matrix. This is called a Hermitian matrix. And one beautiful property of this kind of matrices is that the eigenvalues lambda are real quantities, not complex quantity. Real quantities, right? All the energy, momentum, position, they are the real quantities, right? So that's why this lambda is real. Now, A equals to e to the power minus IHT, right? Immediately, the consequence is if H equals to H star, you can directly verify that A equals to unitary matrix. Because if you do A equals to A star A, that is equals to e to the power minus IHT star e to the power minus IHT, right? So you can directly just do it and you check it is an identity matrix, in fact, right? So all the quantum evolution that you start with the state phi, whatever quantum algorithm you put, whatever you get psi state, another state, right? Whether you do any operations you do, any mathematical operations you do in order to reach your solution, right? And that operation has to be a unitary operation. All this series of gates that will be. One good part is that any unitary matrix multiplication with another unitary matrix will be another unitary matrix, U3. So that means a quantum gate you apply, say, a NOT gate, and another quantum gate you apply, say, Y gate, Pauli Y gate. Another gate you apply at CX gate, for example, right? So this is together, X and Y is acting as a tensor product. It's a unitary matrix. It is another unitary matrix, and multiplication of unitary matrices is also another unitary matrix. That means it is holding the quantum principle. That means you can use quantum gates to prepare a quantum algorithm, to solve a quantum algorithm, to solve a problem. But the essence is that all the gates has to be unitary, and together in the multiplication form or the tensor product form, they should also form the unitary matrix to basically to obey the isolated quantum system solution by Schrodinger, right? So this is how it is related. And so now with this, if you have any question, please ask me, and then I'll go to EVD and SPD part and close it. Alongside these equations, same problems will help to understand quickly. Star is complex conjugate, yes. Okay, this were not from the physics chemistry side. Let me again give you one problem from the, say, network optimization problem. There are lots of network optimization problem. If you can find a Hamiltonian cost function, C of X, for example, cost function, right? Which if you can write in the form, say, it has a Hamiltonian form H, right? And so basically it can be a graph card problem, for example, right? So there are various costs associated. And you have to find the max card or min card. Suppose there is an input and output path, right? So which is the max card or min card path? You can always form a like a optimization problem with X and H as X star HX, this form, right? and you can minimize or maximize this problem, right? And find which is the best card or problem it is, right? So maybe sometime if I get an opportunity, or you will in the other courses, you will see that this equation basically is very common everywhere. This Ax equals to lambda x. Okay. And how you are finding you are solving the minimization problem or maximization problem out of it as an eigenvalue problem. Okay. I did not understand the question. Is there any definition for vector space in a single line? Okay. So single line, it is a vector space is basically a set of vectors, and it obeys basically two principles. It should be vector addition and the scalar multiplications, and you can give example, right? So that's all. Like in notes, I have given detail, but in general, it should obey certain postulates. Like there should be a zero vector. If I add two vectors, that should belongs to that set V. If I multiply it with a scalar with the vector, I get another vector that should also belongs to the vector space V. And these are certain properties. It basically obeys those properties. I said that set of vectors form a vector space. Okay. Okay. So maybe let's start two-part matrix diagonalization. Okay, today I am not giving any proof because 20 minutes is beyond giving proofs, but I'm giving an overview of various matrix factorization techniques. Maybe we'll come back sometimes in later some courses and we'll see the derivations. First, the motivation. Why I should learn the diagonalization techniques, right? Most of the engineering problem, science problem you see, they are typically matrix multiplication or matrix vector multiplications, right? Say, if you have a linear system, those who are from the finance background, you have many variables, right? X1, X2, X3, Xn, right? And they have a relation of the variables that represented by a matrix, right? A econometric matrix. There are certain matrices there that gives the relations of X1 to Xn, and there is something Y1 to Yn are the outcome, right? Or the response, right? Or the market observation. Now, this relationship of the matrices you may know or you may not know, right? So now, anytime you want to estimate this x vector, this is y vector, and this is a, right? So most of the time when you are interested to find those variables, so basically you need to compute the a inverse time the y. And often we see that inversion may exist, may not exist. So this is the one set of problems like linear sets of, can you represent your problem in linear form? Even you do not, even if you at least try to solve some problem where you need to calculate the dot product or outer product, right? Like this kind of thing picture, right? So there is vector multiplications, or sometimes quantum gate or quantum operator, right? Or the e to the power ist that I told, right? This is another matrix basically. So u time the quantum state phi, right? So there is a matrix time of vector multiplications, right? So these are the typical operations we do. But if there is a matrix A and there are elements A11, A12, A1n, and this is ANN, and this is AN1, right? There are n cross n number of elements, right? How many elements? N cross n number of elements. So this is roughly n square, right? N cross n means n square. N square elements. Some of the elements might be zero sometimes. Those where there are many zeros in the system, we call those system as a sparse system. Sparse matrices or sparse systems. This is also in many situations we see sparse system, but in general, if it is a dense system, there are n square element, right? So if there are n square elements in the matrix A, right, and you want to multiply with a vector x, right, it has n elements. So how many operations you need to do? N square times the n, right? So on an average, right? So if it is a matrix times the vector multiplication or a matrix times the matrix multiplication, we'll see it is coming order of n squared to order of n to the power 3, depending on sparsity and other things, right? It's an n square or n to the power 3. That means I have to access all the elements of the matrix A11 to ANN. And there are many elements, right? All the elements I have to access. If I want to multiply these things, so all the elements of this first row has to multiply with all elements of this vector. Then this row with this, all this again and again. So there is a huge computation, right? Huge computation. Huge computation means a huge time loss, huge memory, and huge money, right? Cost. Because you need to spend energy, right? To run your machine, right? So that's why people try to find, is there a better representation of the system, right? Such that I can minimize time, or I can minimize the memory allocations, or I can minimize the cost, right? So one is the direct form, right? Now, can I make it a form like instead of full form, can I remove half of the element? And only I want to represent with this kind of thing. So there is a, if A is a direct form, you can always represent as L equals to LU form. That is a lower triangular matrix times a upper triangular matrix, this form. Then half of your computation saves if they look similar, right? Some of the elements are there, but other elements are only 0. So there is a derivation like using Gaussian elimination methods, Gram-Smith and other things are there. I'm not going to details of that, but in general this way, right? If this A matrix is symmetric matrix, in fact, if it is a SDP, basically semi-positive semi-definite matrix, matrix means x times a x, these particular things, the value gives greater than equals to 0. That means non-negative eigenvalues if it can create. Then A has a better form. This LL means this part and this part is same. Then this part you may not need to compute. LL transpose. This is called the Cholesky decomposition. I'm giving you the condition where which is applicable in which situation. Decomposition. Right. Similarly, A matrix, if you can represent in orthonormal form, that you make these are the general column vectors of the matrix A. But if you can convert these columns of the matrix in such a form that whatever columns you get, the ordinary columns are say A1 vector, A2 vector. These are column vectors, A3 vectors, AN vectors, dot dot dot, and you convert to Q1 vectors, Q2 vectors, dot 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 Qn, such that at this point of time, Q1 is orthogonal to Q2, is orthogonal to Q3, and orthogonal to Qn. Then you create a transformation of the matrix A equals to Q into R, where Q is an orthogonal matrix. Orthogonal matrix means the column vectors of the matrix are orthogonal to each other. In fact, they are orthonormal. And R is a upper triangular matrix. That means it looks like this. These are orthonormal basis vectors. And this is the upper triangular matrix because all the lower triangular values are 0. This is called as QR decomposition. Yeah, so this all leads to the fast algorithms. Yes, thanks. So now this the initial problem was what? Calculating the x, right? That is A inverse B, right? Now, in many cases, that A may not be in fact, A may not be a square matrix. It can be a rectangular matrix, right? So calculating this A inverse that time may be very difficult. Means there is a rectangular system A, and there are few variables, x1 and x2 or x3, some few variables are there. Then there is some, accordingly, you may have some y1 to yn, this kind of system where there are like A is fat and x is very small and y is tall, right? This kind of system you may get. And then for a rectangular matrix, this A inverse does not exist, right? So for that case, there is a solution called a least square solution. in fact, right? So I'm writing the solution now, but maybe someday later I'll give a proof. The proof is not difficult at all. A star A whole inverse A star B. So basically, instead of calculating A inverse, because A inverse does not exist, so you calculate the A star A, that becomes, even if it is a rectangular matrix, say the dimension is 4 cross 2, right? But still 2 cross 4 cross 4 cross 2, that becomes 2 cross 2 is a square matrix. That's the intelligent way of doing it. But of course, there will be some errors coming from this picture. Times the A star B this way. This is called the least square solution. And now we just learned that A can be represented as QR inverse B, right? So that means earlier we were computing how many elements? N square element. But Q is a very standard matrix. It's a orthogonal matrix. You don't need to do much here, but you need to calculate the R inverse part, right? It is basically R inverse Q inverse P, right? You need to just calculate this part. This part is straightforward. So this part means you almost remove the half of the element of the matrix. It's the upper triangular matrix, right? So lower triangular will be basically there are elements, and these are all 0, right, for the matrix R. Okay, so that's how you almost reduced half of the cost for calculation the inverse problem. Now let's go a little bit more. Just sometimes ago, before, we have learned Ax equals to lambda x, right? And we have also learned that there may be many such x, right? So a1 x1 equals to lambda 1 x1 a2. This is not the direct proof. The direct proof is a different way. There are algorithms like GKR and other things. I'm not going toward that direction, but in simple way, I try to show it. Suppose a1 x1 equals to lambda 1 x1, then a2 x2 no. So a is common. So the a is common, right? A x2 equals to lambda 2 x2, right? So now I can write this equation in this form, right? So if I combine these two equations, so it will be, let's take a common, x1, x2, right? And I can write this lambda as diagonal matrix, lambda 1, lambda 2, 0, 0. And I can write it as x1, x2, right? Now you can extend this matrix like a times, say, x1, x2. These are orthonormal vectors, right? x3 dot 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 xn, and it will be your diagonal matrix lambda 1, lambda 2 dot 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 lambda n times this particular case. The case is x1, x2, and so on, right? x1. So I need to check the dimension. I'm just writing it here. So you just split the equation. Say, for example, a1 x1 equals to lambda 1 x1, a2 x2 equals to lambda 2 x2, a3 x3 equals to lambda 3 x3, and so on. So you can come back from these equations to here. Now, if they are orthonormal vectors, basis vectors, so what we can do? So this all together, it is forming a matrix, right? Because if it is n cross n matrix, now it becomes another n cross n matrix, right? It becomes another n cross n matrix. It becomes another n cross n matrix, right? In that case, what happens is you can call it is A equals to this matrix you call A equals to U, okay? Equals to, and this big matrix you call as capital lambda, okay? And this you call as U, okay? A equals to lambda U, okay? And then you do pre-multiplication with that U, and you can get, this is a constant quantity. You keep it in the left side, and you can do this U star U. Now we know that U star U is identity matrix, so equals to lambda, right? So this is one way of writing, or also you can write it as AU equals to lambda U. Similarly, you can do post multiplication also. A equals to lambda U star, means left side you multiplied U and U star. So sorry. So this way you can diagonalize a matrix. So it becomes a diagonal one because the elements are lambda 1, lambda 2, and so on, right? So vice versa, you can write a matrix in this form, U, lambda, U star. Just you do the multiplication in the reverse way here, right? So this is called the diagonalization of a matrix. So there is a orthonormal matrix, diagonal matrix, and one basically orthogonal matrix, right? Or unitary matrix, basically you can say. So if the quantities of A are complex, then it becomes a unitary matrix. If the component of A are real, then you can write it as Q lambda Q star. This is also diagonalization, but in this case, Q are the orthogonal matrix. Okay, but the condition to reach this part, because earlier we had n cross n element operation. Now it is we are working on lambda. It is only n cross one element. So it will be much faster. In fact, if you get these things, you get all the energy spectra of a molecule of any quantum mechanical phenomena, right? So means we started with a matrix with many elements, but we reached to a matrix which is only has the diagonal elements, right? Because these are beautiful. U and U star, they have good properties, unitary matrices. So what we need to understand only the elements in lambda, right? And the condition to have this kind of decomposition is that either A has to be, okay, I am running out of slides. Please allow me. Just 5 minutes. Yeah. So we can represent a matrix in this form QR, that is orthogonal matrix times the upper triangular matrix. We can also represent the matrix. This is for any ordinary A. If A is special, that means AX X star greater than equals to 0, then A has a better form, that A equals to LL transpose form, lower triangular times upper triangular with the same matrix. Is called the Cholesky decomposition of the matrix. This is called the QR decomposition of the matrix. We can also do U lambda U star form. This is called the eigen decomposition form of the matrix. Here it is diagonal, and we are only acting on n number of element instead of n square element. We are only working on the n number of elements. So this is diagonal matrix. But to reach there, you need additional condition, either A equals to A Hermitian, that means A star, else the better condition is A star equals to A star A. This kind of condition is called the normal matrices condition. Normal matrices. Okay. For normal matrices, eigenvalue decomposition exists. For positive semi-indefinite matrices, Cholesky decomposition exists. If there is no condition, then you can go for the QR decompositions, right? Now there is also another form that is called the SVD, singular value decomposition. Value decomposition, where if A is some ordinary matrix, in fact, it may be square, it may be rectangular, any ordinary matrix. That case also, I'm not giving you the proof, but A matrix you can represent as U sigma V star. Now this is one unitary matrix. This is another unitary matrix, another different unitary matrix, and this is a diagonal matrix. Diagonal matrix. This time, this U and V star are unitary, means U star equals to identity, V star equals to identity. This property hold, as well as this is diagonal, means this has certain diagonal elements, sigma 1, sigma 2 to sigma n, right? So you can also do the ordinary matrix. Now you can ask me, if I can do SVD for ordinary matrix, then why shall I go for the eigenvalue decompositions, right? Because it needs more conditions, more constant. The part is the eigenvalues this you are getting, you have two options. You can get real values for what? For Hermitian matrices like Hamiltonian. you can get complex, like you have the phase information of certain system, right? Complex values for non-Hermitian system or any ordinary system, right? You can get the complex eigenvalues. So phase information is there with your eigenvalue decomposition. But with singular value, whatever singular values you get diagonal matrix, they are all real quantity always. Right? Now there is relation between EBD and SBD. I'm not going in this particular course, but you have some understanding. Okay, I can do diagonalization of a matrix using techniques like EBD and SBD. For quantum, EBD is more prominent, is a more suitable form, directly coming from the ordinary differential equation solution of Schrodinger equation. And that's why eigenvalues are so important. Even later, you will see that quantum measurement gives you the eigenvalues of quantum operators, measurement operators. Okay. With this, I am concluding this part, and please let me know if you have any questions.
Participants are requested to post their questions in the chat box. So raise your hand and we will unmute you in case if you want to speak.
Can you explain raised power of a matrix? Raising power of a matrix is just raising power of eigenvalues. There is a theorem called Hamiltonian theorem, CH theorem, and you can prove that just powering a matrix, it's same as powering eigenvalues. Now you see, just if you multiply a square, say a square means 8 multiplication with a. Now you have n square element times n square element. How many computation? Huge time, huge memory loss, right? Huge energy loss. But if you somehow can do the eigenvalue decompositions, right? You just need to do a scalar square, like say the eigenvalues diagonal elements, right? Only n cross 1 are diagonal elements. So you need a very simple scalar multiplication. Matrix multiplication becomes your scalar multiplication. Huge energy save, right? And time savings. UBD and SBD notes, please. Maybe, sir, we can keep it in QT3 or sometimes later, right? This is much advanced topic. So I just touched everything as part of, following the syllabus. Yeah, this is a bit difficult. I understood for some of the scholar. Please repeat the thing with the notes and
Sir,
all.
you are on mute, Pillai sir.
Pillai
Yeah,
sir.
Mustafizur sir's 2-hour lecture means full 2 hours. Yeah, notes will be shared and the handwritten notes also. Mustafizur sir, I'll request you
I'll share.
share the slides so that. Yeah, actually, I really like the way that he puts forward mathematics so easily. Everybody is refreshed.
I try to connect physics, engineering, chemistry, math, everything. I try to appreciate the audience because the main you have a lot of information over internet, many learning resources. The only thing that learners like me or anybody feel problematic is the connection between them, like how these things are connected, how these things are applied. I hope they will get more and more such things in our forwarding lectures by other experts as well.
Yeah, Shubhakarji, you want to say something? I think I am not the admin, so I'm not able to unmute. Anyway, you can write in the chat. It's very important. Then I'll ask the admin team to unmute you. Yeah, I'm sitting in my office, so.
Sir, hello, sir. It is unmuted now.
Right, we have unmuted him.
Yeah.
Can you
Good.
hear me, sir? Rahman, sir?
Yes, sir.
My question was E raised to the power of a matrix. You mentioned E power minus I H T.
Oh, that one. I see.
Ah.
Yeah. So what is the question, sir? Here?
What does it mean actually? E raised to the power of a matrix. A
Yes,
matrix
yes.
sitting over E.
I am giving you a just very short answer, but in fact, there are stories of this. This is called the exponential function of a matrix. Okay. And there is a I sitting there. That is also another role, imaginary part. But the thing is, e to the power of a matrix is another matrix is basically it is a like e to the power x. I say e to the power x. If x is a variable, then you can expand in the Taylor series form, right?
Yeah, that right.
X plus x square by 2, so on. Similarly, e to the power a is a matrix, then e to the power minus of a or e to the power a, that is also a like exponential series expression. A plus a factor a square by 2 factorial, a to the power 3 by 3 factorial. But this time a is a matrix here. So altogether, if I have an infinity memory, I can store all the values. So I get a matrix e to the power IHT, that is another matrix basically. But it is not as like a matrix with individual component e to the power IA11, IA12, not that case. This is not the case.
Yeah, thank you, sir.
Thank you, sir. Yeah, sometimes we do not understand question just by seeing chat. That is also an issue. Yeah. Yeah, so some books, the plenty of books. One is those are very new to the algebra. I will suggest, please, if you have some times, 30 minutes a day, 20 minutes a day, lecture series by Professor Gilbert Strang on YouTube and or MIT OCW. Linear Algebra Introduction by Professor Gilbert Strang. He recently retired from MIT last year. I really fond of him. Like I learned everything from him initially, and still I learn things from him. That is the basic book normally taught in UG level. Linear algebra books also there. The 300, 400 rupees books is written by him. Like it's a Nobel, like a book for linear algebra. Once you are good with that, there are books like the advanced stage, like Horn Johnson book or Wilkinson book on especially on the norm and various aspects of linear algebra. Once you are familiar with that, you are more concerned about eigenvalues, quantum computing, this stuff. There is an advanced book called Golub, basically Golub and somebody else, I forgot the name, but Golub it's basically. And then there is book by more advanced book is also there by Said Yusuf from ETH Zurich. Okay, so I will suggest to start with the Gilbert Strang. That's a very fundamental, very basic book, and you will be amazed how that like Professor Gilbert Strang taught this linear algebra course. It is, I'm telling you, like technology will change in every 5 years, 10 years, right? But mathematics and physics does not change, especially mathematics like algebra, optimization, and probability theory. Once you learn, it will be ever in your life. Every time any technology comes, you can relate, right? So whether it is quantum computing, cloud computing, something other AI or new something DNA computing in future, for example. So every time these mathematics will be useful. So it's a one-time investment only.
Thank you, sir.
Thank you so much. Maybe, sir, we can.
Yeah. Maipal, you can conclude.
Thank you so much, sir, for explaining this, one can say, difficult concepts very smoothly. And what I request to the participants that you should not directly look for notes. Of course, we are sharing it, but what I request them to start from scratch, pick a blank paper and try to recreate the entire lecture of sir. And in between, if you struggle, then look for the notes. So that way you will be able to learn even more. That is my recommendation. Thank you.
Yeah,
Thank you,
just
sir.
to add something, please don't worry again. The content it will take time to digest. Please understand that, right? Dr. Mustafizar has been repeatedly telling he's trying to connect so many things so that you will all get interested. So please be patient for some more time, right? Let the mathematics and then digital, like everybody, when computer topics come, computer science teachers will be active. Now suddenly today maths teachers must have been very active. Yeah, or very nice. The way that so you please understand that everybody, like somebody who is doing now tomorrow physics will come, then physics faculty will find it very easy, right? So there will be different steps. Now statistics he will teach. Now the commerce people and all, they will feel very easy. Oh, okay, this is our content, right? So after this, then we'll actually go into quantum technologies and applications, where basically the understanding of what quantum is and all will be explained, right? That is QT-01. These are all basics that we are doing as a prerequisite for that. But still we are doing it at a slightly higher level because you are all faculty members.
Yeah.
We are not teaching like students. You please understand, Mustafa sir's presentations are aimed at teachers because you have studied somewhere, right? So please refresh that and take his notes, as Maipal rightly pointed out. Please look at and refresh your notes. Some of you are making comments that, yeah, our college ke din yaad aa gaye. We are remembering our Marapura college rojulu. So you're all remembering those days. So I hope you will all enjoy that. And please be patient. Go slow. Don't worry. Don't feel depressed. It will take some time, right? Quantum is difficult. Everybody knows. So let us take it step by step. And he's putting a lot of effort. He's prepared again slides for you today, again fresh. Every time he is thinking and coming with different ways to present the content easily so that you will understand. So we should appreciate sir's time and effort, and also that we all want that we must not be afraid of quantum, right? So please, otherwise we are failing if we don't encourage you to do that. So hopefully please continue, and please tell your friends that slowly, as we do the basics, we will start understanding, and you will appreciate why you are doing QT-00 before QT-01. You are fortunate because QT-01 people did not have opportunity in our MNIT series. QT-00 was not there. This content was not taught. So you are lucky, and so we'll, I think, Maipal, we'll meet tomorrow at 3 o'clock. Right?
Sure, sir. Yes.
So we'll continue.
Sir, thank you very much.
Yeah, thank you so much.
Thank you, sir. Thank you so much. One more small announcement. Those who have to pay the registration fee, please pay. Only 250 people have paid. So there are 1,000 people in the group. So please pay the registration fee and complete that process so that we can issue the list, right? Thank you so much. Yeah, Anil sir, would you like to add something?
No, thank you, sir. Thank you.
Right.
So only our wish is to onboard all the 1,000 participants.
Yes, sir. Yes, sir. We'll slowly send one reminders
Yes,
that
sir.
you have not joined. So we are just waiting for till today. I'll place in the group also that please pay the registration fee and complete that. So once those who have not completed, then yeah, please remember that you can attend the lectures. We will not stop you. You will keep continuing to get the slides also. Will not stop you. But certificate will not be able to give you if you do not pay the money. Right? Please understand. That's the link. So you can do that. We have no problem. The QT-01, 02, 03, 05 and 06 video recordings are open. They are on the YouTube. If you want, you can follow them. So we have no problem with registrations, freely attending the course, no problem. If you want the certificate, that's where you have to pay. So please complete the registration immediately after the course. There are few problems still we are addressing, WebEx and Canvas. So please, we are available. Maipal sir is also available. So please post your questions to us, and you know our numbers now. So you can write the questions to us. We'll try to slowly answer and one by one. And if there is a large number, then we'll conduct another orientation session. Thank you so much. We'll meet tomorrow at 3.
Yeah, bye.